In this video, we are going to explore about the ARM processor memory organization. So let's recall the last class topic. In last class, we are discussed about the ARM processor architecture that includes the power efficiency, memory management, architecture and design of ARM processors, and instruction set, interrupt handling, and the development tools. Now let's see about today's topic for discussion. So today we cover the four main topics, that is ARM memory architecture overview, understanding memory maps, Raspberry Pi GPIO memory mapped input output, endians, that is a byte ordering in memory. Now let's move on to the ARM memory organization, unlocking system performance. Why this is so important? A deep understanding of ARM memory is critical because it directly impacts system performance, reliability, and your ability to debug effectively. This knowledge is essential for both bare metals and OS level development. And now let's move on to the ARM memory architecture overview. So it's begin with the RISC design, that is a reduced instruction set computer architecture. So the ARM uses RISC design for optimized for simplicity and efficiency in embedded systems. So it supports both hardware and von Neumann architectures, offering flexibility. Furthermore, advanced Cortex-A features an integrated memory management unit. So it includes an MMU for virtual memory management and a cache hierarchy to dramatically speed up memory access. Now let's move on to the empathize part of our design thinking, that is understanding the memory maps. So think of this as the logical layout of your system address space. So it defines where RAM and ROM and peripherals to live. For instance, on a Cortex M4, a flashlight starts at 0x0 and SRAM starts at 0x260. Peripherals get their own decided address and allowing software to control hardware directly through simple memory reads and writes operation. So now move on to the demo part of Raspberry Pi GPIO, memory mapped input output. So let's see this in an action with the Raspberry Pi. So its GPIO is controlled via memory mapped input output. The base address has changed between models at 0x3F2 for older pins and 0xAF2 20 for the PI4. By writing to register at offsets from this base, like the function from this select register, we can directly set a pin as an input or output. So this will giving us a fine-grained hardware control. So now let's see about the endians for byte ordering in memory management. We know that endians defines the byte ordering in everywhere. So it defines the byte order for multi-byte data in memory. So in little endian, the least significant byte is stored first. In big endian, the most significant byte is stored first. And ARM processors are bi-endian. That means they support both the little endian and big endian modes. But default it will take a little endian one. So now let's see the endians example. So here is the data value concrete 0x12345678. So the little endian stores the least significant bit first, that is 78 first in the first addressing mode, that is 0x1000. And the big endian stores the 0x12 the MSB first. The next addressing, the little endian stores 56 and the big endian stores the 34. And finally, the LSB is 78, big Indian stores 78 and the little Indian store 0x12. So, this is why understanding Indians is vital for data communication and interpretation. So now see about the memory alignment in optimizing access. So in this, the data should be stored at addresses that are multiples of their size. A 4-byte boundary like 0x100 or 0x1004, this allows the processor to access data efficiently in a single cycle. So misalignment can cause huge performance penalties or even hardware defaults. And consider a case study, that is misaligned memory access crash. So consider this case study, that is casting a character pointer that is to an integer pointer on an odd address. In older ARM chips, this caused an immediate crash, but a data abort. Even on modern cores that handle it, the performance cost is severe and the debugging the result data corruption can be nightmare. So next move on to the ARM assembly load store alignment. So we know that the LDR represents the load and STR represents the store instruction. So these instructions are used to move data between registers and memory. So these instructions are most efficient with properly aligned addresses. When debugging tools like GDB are essential in C, we can use attributes like aligned and packed to manage alignment explicitly. So now let's see about the mind map of this process. So to bring it all together, this mind map shows how memory architecture maps, endians and alignment are interconnected concepts that are complete picture of ARM memory organization. So now let's move on to the conclusion part of this video. So in conclusion, mastering this ARM memory fundamentals is a key to building robust embedded systems. Memory maps are blueprint, endians ensures correct data interpretation, and proper alignment is vital for performance and stability. So now let's the time for assessment. So if the 32-bit hexadecimal value 0x12345678 are stored in memory, starting at address 0x100 using a big endian format, what byte will be found at address 0x1001? So that is 0x34 is the correct answer. These are all the references. Thank you.